Hi everyone, I'm Mark, and I'm going to talk to you today about what it means to develop code in a way where you're absolutely certain that you haven't broken anything when you're at scale. So local decision. In any code base of your choice, you're making a diff, you're making a change to the code base. And this talk is about reasoning locally without having to know the global state of every single project in that repo. Did I break stuff? That's what we're going to be focusing on today. I should tell you, this is a tooling talk. This is not a nitty-gritty C++ talk. There is not a lot of code here. The code that is here is very simple. Just going to give you that heads up. This is not, for example, my colleague gave a talk on strings at Facebook yesterday. That one is a great one if you like that stuff. I enjoy that stuff myself. It's not this talk. This would be more about if you make a change to string, how are you sure that you didn't break stuff? So with that, I want to open with a few questions that I think are relevant to every engineer in every repository that they work in. And it's stuff like, how do I know if my code is broken? Is I think a very important question. And I will assert right now that it is insufficient to say it compiles, it links, and it passes all of its tests, therefore it must be correct, it must not be broken. I think that is an incomplete definition of broken. And to give you a couple of examples as to what I mean by that, things that could be broken beyond that definition. Undefined behavior is a big one. So non-determinism. If you've got some non-determinism in your code, you run the tests are great this time, maybe not the next one. I think that that code is broken. So running the tests, insufficient. Here's a more kind of atypical definition. Maybe it just doesn't do what it was supposed to do. The client wanted this thing, you gave them that thing. Do we call that broken, yes or no? And they have very different answers then to how do you know if it is broken, right? If it's compilation that we're talking about, I can tell whether or not it's broken by just checking the return code from GCC or Clang. Very easy, I know whether or not it has broken. Is it what the client intended? That's, human, arbitrary, perhaps painful. So it's very interesting, it's very different. And these questions all tie together. And knowing why something is broken, turns out, is incredibly important to answering the very first question I have on this slide, which is, how do you prevent code from being broken? Here's a spoiler. It turns out, even if you have the answer to every single other question on this slide, that is insufficient to prevent code from breaking. It is not enough to tell people whether or not it is broken. It is not enough to tell them why it has broken. That will not keep your code base golden. That's insufficient to do that at scale. Now, let's talk scale. Let's talk perspective here, because a lot of these are very easy when you're dealing with a small scale. If you want to know, is my project broken for a small scale, maybe something on GitHub, maybe even one of the compilers themselves, let's say Clang. It is totally reasonable for me to take all of the tests of Clang, build the entirety of Clang, run all of the tests of Clang on this laptop right here. I can do that, I can go have lunch, it'll probably be done by the time I get back. That's a reasonable thing for me to do. I can even run them with address sanitizer and all the other sanitizers. I can do that. We have thousands of developers, hundreds of thousands of files at Facebook, and one repo that contains almost every C++ project with dependencies all over the place. It is intractable for me as an engineer to, on my box, on even a couple boxes, build all the things that I might need to build to test my changes. And I just can't do it. And what makes this even more interesting, we have pressure to keep things from breaking because we're pushing code out the door all the time. All of those projects which have dependencies all over the place, are being pushed all the time, right? They all have their own release schedules. Things are flying out the door left, right, and center. So things that might be simple at a smaller scale, just keep that in mind. Things get complicated when you're bigger. I want to open with an example of the kind of change I'm talking about. And this is a change, or it will lead into a change that I made when I first joined the company full-time that had quite a big impact on the code base. So this is a terrible test, but here it is. I've got this enforces 5 function. It rejects any number that isn't 5. I've got a Google test, G-test thing at the bottom there. It calls it twice. One time it's OK, one time it isn't. Run this with standard G-test, and you're going to get something like the following. Right? It's kind of like an assertion. It tells you, hey, this wasn't what we expected. It tells you the line number. And that's OK. That's actually pretty good. It tells me, the first place I should be looking. But now suppose instead of one test that calls this, I've got in my single file 50 tests. And they all call enforces 5. Some of it do it through different roundabout code paths. How did I get there is kind of an important thing. And so the obvious thing that I want is a stack trace. I want to know exactly what led up to being in that enforces 5 function that triggered that assertion that caused this failure, that caused my program to terminate. And this is a no-brainer win. We have had, for a long time, we have an open source library called Folly. It is our flagship C++ library, well worth taking a look. There's some documentation in there. But one of the things that it has is this Folly symbolizer, this signal handling stuff. And what that does is with a couple lines in your main function, now anytime one of these expectation goes off, anytime an assertion goes off, and a few other different kinds of errors, bam, immediately, stack traces just automatically print it. And that's amazing. Let me back up for just a second. Suppose that this test was running on a different machine, one that maybe had a slightly different environment than the one that I normally work with. And it crashed, and it produced this error. Now, if I look at the logs, I have total context of what went wrong on that box. I can open up my editor straight to that line. I don't have to repro it to say, hey, here's where the problem is. And what's more, maybe I can't repro it on my machine because it's non-deterministic or my machine setup is slightly different or whatever else. So just having this information just automatically be printed anytime it fails turns out to be incredibly useful. I saw a question in the front.
Yeah, does it work on Windows?
Does it work on Windows? It probably does, but I can make no promises. I know we're trying to be better about having that work on Windows. So, no-brainer win. We want this as opposed to this. All right? There's a catch. And the catch is something I've already mentioned, and that is that to have this, you need to have 2 lines in your main function for your test. And that's every test. And that's every test in a code base with hundreds of thousands of files, and you can imagine how many of those are tests. Right? That's the number of main functions that then need to have the 2 lines that it takes to turn this on. But it's a win. It helps us all over the place. And so the question becomes, how do you get that? Education is not an option, because thousands of developers, you can't educate them and expect them to remember and to just always do the right thing. You can add linting, and that's a pretty good solution. For us, we were in kind of a unique position where our build tool, if you don't provide a main function for your tests, we link one in for you. That main function happens to be the default one that ships with Google Test Framework. I believe that only looks like initialize the Google Test Framework, return, run all the tests. And so one of the first diffs I made at the company was this. Take that Google Test main function, throw the 2 symbolization lines in the middle, plus a couple other things for correctness, and bam, I've just made all of my error messages better. Now I want to take a step back for a second. This is a small code change, but the impact of it is changing every single test in a code base with hundreds of thousands of files, and you can guess how many tests, right? Massive number of things have just had the rug swept out from under them, their main function. How do I know that that's okay? And by the way, the one arcane bit of C++ you'll see in this talk is on this slide. It's the attribute weak. That's the part that says, if you have a main function, use that one, otherwise use this one. So back to the question. How do I know if nothing broke? Well, the first level of did I break stuff for me was pick my favorite test, the one that compiles the fastest. Run that. Sample size of 1 has to be good before I can worry about corner cases. And so I pose to you now, Hans, how would you check a change like this? How would you make sure in your code base that nothing broke? Not that something didn't break, but that nothing broke. Any ideas?
Run all the tests throughout all the projects you have.
Run all the tests. Great. As I mentioned, cannot run all the tests on a single box. Would take too long.
Sometimes it takes a distributed environment.
Yeah, so great. It sometimes takes a distributed environment, and indeed, I'll talk more about that later. We do have one. We shard off to a bunch of different machines, different builds, build everything in parallel. You can get that answer pretty quickly. Any other suggestions for how you might test this? So we have over here a suggestion to take a sample of the tests, and you can get statistical confidence for whether or not you broke something. Yes?
What if you determine the code path that was affected and just run tests that test that code path?
So the idea was we figure out the code path of the things that were affected and just test that. In this case, with this particular change, that's everything. So we're now worried about running all the tests. And by the way, I want to give another example to motivate this. Nicholas yesterday was talking about how we have our own version of standard string. We replace standard string with one called FB string, also found in that Folly open source library. And if you make a change for that, string is the most included header at Facebook. And so literally everything is going to be affected by that change. And again, how do you test it? That's a very subtle thing that everything depends on the behavior of. Yes?
Just check it in and have some smarts in the build system to reverse the change if it detects some breakages in the projects that are completely unrelated to you and far away from you.
So the suggestion was to have a smart build system that was aware of the projects that are related to you and not. And I might have missed some in the middle.
Yeah, I'm saying just don't rely on any testing on your local machine. Just put it in production and then have an ability to revert the change if it breaks.
Okay. So we have a suggestion to just push the code and revert it if it turns out it's bad, which is potentially okay depending on your model. I know some people who do that and are very successful with that. But for us, we were trying to keep trunk clean. So I'm going to move on from this question and keep going. So this is where that example kind of peters off, right? It's just an example that was there for scope, to be thinking about the kinds of problems we're trying to solve. Diffs that affect large amounts of the code base, they do happen. It's not like once in a blue moon. It's, there are people who make those changes. So we need to scale that. And the fundamental problem here is a single engineer cannot reason on their own about the entire repository. You have to make it so that it is a local problem. And what that means is you need automation. There needs to be some level of automatic code review. And I'm going to talk about different pieces that we have that make up automatic code review that do take this from a global must be aware of the entire system, which is intractable at our scale, to just need to reason about my change and whether or not my change is correct. And one of the first things that we have that does that is linting that shows up at code review time. So the image here, the green part, the background, is a version of the open source tool called Fabricator. It's a code review thing, not the part that I'm most interested in telling you about. The other part is in line here. When you toss up a diff for code review, we're just going to tell you, hey, you've got clang warnings. This is probably bogus, right? And suggest a patch is even better. Beyond clang warnings, we've got linting. One of the first things that bit me when I was an intern a few years ago at the company was I had a lock guard, and that lock guard didn't have a name. And for those of you who've been bitten by this, I'm sure draws back some painful memories. But basically what goes on if you have a lock guard without a name is you construct it, and you immediately destruct it, and then you have the thing that was supposed to be your critical section, right? And that's kind of tricky because it does drop some, fancy memory compiler stuff in there. And so it's mostly right. It does the thing that you expect it to do most of the time, but it's in fact a bug in your program. And so we get burned by that once. We add a lint rule, shows up on your diff, right? That's code review number one, automatic. We get bitten by something once as a company, we codify it up, goes away forever. Thing number two is the distributed build. So I mentioned before, we don't build everything locally because you just can't. You really just can't. And so what we do is we have continuous integration. When I want to know if changing standard string broke anything, we build everything. Our continuous integration system builds exactly the set of things that are transitively impacted by your change. So if you do change standard string, that's probably the universe, but if you change something smaller, then it intelligently scales down and all of the good things that you might expect. And it will tell you, did it build fail, test fail, is it successful? The gray category is kind of a weird one that I might get into later. And this is where things get interesting. Because if all I did to construct this screen was give you the return codes of the tests and the return codes of the builds, we'd be in a bad place. And for that, I want to tell you a story. And that story is of what is now quite a few years old. So when I was first an intern at the company, this is a few years now, things were bad, right? We've come a long way since then, and the way code review used to work is I would toss up a diff and it would kick off a bunch of different builds, but I would just expect a bunch of them to fail. There was a percentage in my head that was like, I don't know, maybe 20%. If I am looking at a diff and only 20% of the things on it are red, have been broken, and we only had one kind of failure, just big old red failure, 20% was okay. Like, I was going to ship that diff because that's the amount that I expect. And that sucks, because if there is a real problem in that 20%, I would have just ignored it. Nowadays, we do a lot better. And the reason why a few years ago that was the case, where there was so much noise, is because if all you do is tell people whether or not the code is broken, then you're not telling them useful information. You're providing global state information. You're telling them anything that was broken in the repo, and you must assume in a large enough repo that something will always be broken. There is no such thing as a perfect repo, as a totally perfect golden repo at this scale. Your system has to account for things are just going to be broken from time to time. What the person who's writing the code change wants to know is, did I make this any worse than it was before? Green means nothing new. Nothing new is broken. It is equally or less broken than it was before I made my change. That's what people care about. And so that's kind of an interesting thing. And the way that we do that is we say, okay, if a test has failed on your diff, we go back a revision and we run that test on that revision too. And if it failed there, we're just going to say you did a good job. Right? Local decisions, that's what we're going for here. That's how you scale code review. And the other thing about this is, that makes this hard, is suppose I have a test that fails 1 in 1,000 times. 1 in 1,000 seems pretty good. Now multiply that by the number of tests in a code base with hundreds of thousands of files, and 1 over 1,000 is beginning to look a little, it's looking pretty big. Right? That's the number of spurious failures you can expect on a diff. Right? The number of things where when I run the test on my diff, it fails not because I broke it, but because it had some undefined behavior, and this particular time when I ran it, it showed up as bad. I go back a revision and I say, hey, it was good before because I just got lucky that time, and I blame you now. I blame the author of that diff for causing a problem that they never caused. Right? It ruins trust, and that's where the 20% number comes from. The person just assumes that there's an amount of brokenness in the system. So how do you deal with that? We have these things called wardens. And what the wardens do is they identify flaky tests, the tests that are not perfect. A perfect test for me is one that in trunk is always green, is always passing, 100% of the time. Because if it breaks, we want people to see that it broke, fix it, and then land their diff and have it continue to be green. Right? It should never be read in trunk. That's a perfect test. I think the next best kind of test is the one that is always read, the test that always fails in trunk. Right? That's kind of counterintuitive, perhaps. But if it fails on my diff and I rerun it on the revision from before that, and it failed there, I'm not going to blame you. And so that's good, right? Maybe we're not getting any benefit from it, and we could if we fixed it, but at the very least, it's not getting in the way. The tests that make my life, let's say, interesting are the ones that go green, 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 red, green, green, red, red, green. The ones that flip-flop, with any pattern, with any amount of time in between. The ones that just spuriously fail every now and again are the ones that cause trouble when you scale up, when you multiply 1 over 1,000 by the number of tests you have. And so that's where the wardens come in. The wardens identify this from the history. They can run stress tests that make these more likely to spuriously fail. One way or another, they figure out which ones are the bad tests, tell people, and turn them off. Because a test that only works 1 in 1,000 times isn't good enough. It actively hurts the health of the code base because people ignore the tests that pass all of the time. Which is kind of a very interesting human problem. Right? This is all about signal and noise. It's a lot of what this talk is about. Is how do you get people to listen to you when you tell them this is broken and you're right? Part of that is not being wrong. All right, so going back to this. Turns out there's some very simple things you can do to address that problem at scale without actually fixing those tests. So one thing I should actually talk about before I dive into this is a test can self-diagnose that something out of its control has gone wrong. Right? A test is there to test a particular thing, and if one of its dependencies has died, it can recognize that. And we have stuff in the code where it can skip, and that counts as it didn't pass, it didn't fail, but it's not your fault. That's also very nice. But if you don't have the wardens that disable these bad tests, or the tests that self-diagnose that something out of their control went wrong, what can you do to make people trust you, to make people listen to you, so that you don't land code that you know is bad? And one of the things that we came up with is add colors. Right? Super simple idea. We used to have one failure category, just red. Build and test failures were both in there. Now we have 2, and the reason for that is that compilers are great. They are extremely reliable. You pass the same code to Clang or GCC a million times, and I bet you're going to see the same outcome every single time. Chandler was saying in his talk the other day, Clang does a bunch of stuff to impose orderings on things that otherwise might not be, just so that it's deterministic. So you get the same result every single time. Even if it's a compiler bug, you should see it all of the time, not some of it. And because of that, turns out build failures are extremely trustworthy. And they're also the most important because they block running tests. And so by categorizing them separately, you can trust them separately. And not trust test failures if we're in the state we were a few years ago, or do if we have wardens and we're better. But it's this labeling that buys you trust. Another thing that can really help without fixing any of the underlying issues with any of your tests is supplying the error message. Used to be, if you saw a failure on your diff, you either knew how to get through some arcane flow to see the logs and then hope you found the spot in the logs with the issue, or you tried to repro it locally and wasted a bunch of your time doing that to potentially find nothing, which sucks. Nowadays, the logs are inline, and not just the logs, but the part of the logs that is the error message. We have a tool that does that, and we continue to find amazing uses for, I can identify which part of a log happens to be the one that is broken. Right? If you picture a database, picture your code base, and now picture a database over that entire code base that has the list of every single error message and how frequently it shows up. You could probably do some damage with that, the good kind of damage. So putting this information on the diff itself meant that for those test failures where trust is an issue some of the time, you can say, yes, this is my fault, no, it isn't, without having to build stuff, without having to worry about will it repro locally, without having to worry about any of that. Huge win. So I've talked to you about automatic code review, and the goal here again is we want to be able to make local decisions about complicated changes that affect the global state without having to know anything about other projects that you don't work on. And the question then becomes, where does the human component come in? Because the human component is the one that you have to scale. Right? The machines, you can throw more hardware at a problem, and it'll scale. I mean, you probably want to do more than that, but the humans, that's the hard part. A human cannot reason about a code base with hundreds of thousands of files on their own. So what's left for them after you've done all these things? And the answer is most of the job of a human reviewer at Facebook is to interpret the results, is to say, hey, you missed something, you should go fix that, or that one's actually flaky, keep going. You can ship this code. The other thing that they do, I call meta-correctness checks. An example of one of those that we have automated, one that we've made scale better, is formatting, right? Every company has some sort of style guide. If your humans are going in and trying to evaluate, yeah, this has the spacing we want and the curly braces we want and all of that, you're probably wasting your time. There's a tool out there called Clang Format, and we have it now as a linter that automatically runs over all of our code and just fixes it before it ever goes up for review. So it's consistent across every engineer automatically all the time. That's no longer something that a human has to do. That is something that is now scalable out to however many engineers without having to individually educate any of them on what the style is supposed to be. Other things that might be in there are, does the code do what it was supposed to do? Does this code actually do something that, does it achieve the goal it was trying to achieve? And I'm curious, what else do you think falls to the human in a world like this? What does a human still have to say, yeah, this change to the code base is a good one? Ideas?
Well, on a higher level, you might solve a particular problem in multiple ways, and your design might be worse than something else that might be suggested.
Yeah, so the thought was, you might solve the problem, but there might be a better way to solve that problem. And an example of that might be yours is less efficient than an alternative, right? Maybe you're using the wrong algorithm. Anyone else have ideas for things that a human might have to check?
Someone would be committing a change to the way the tests are run or to the infrastructure itself. So it might also be something like meta.
Yeah, so someone might change the way that the tests themselves are run, and that could be a meta check. A good way to check that is to just run all the tests and see, did it break the tests, or the way that we interpret the results of the tests, or whatever else it is you're affecting. So that can often be done automatically. Yes?
You could check that variable and function names make sense and communicate the ideas of the code.
Yeah, so we want to make sure that the names of things in our code are self-documenting, that they accurately reflect what's going on. And that's harder to check with something like Clang Format.
Security and malicious behavior outside the bounds of the test.
Sure, security and malicious behavior is a great one. You can catch some of that with automatic tooling like fuzzing, but not everything, of course. And so that kind of check is still human. Now, this is an interesting thing because the more you grow, the more things you absolutely want to remove from meta-correctness checking into automatic. And an example of what I think is a really cool one, sorry, it's not in C++ these days, but in D, Andrei Alexandrescu is currently working on a big O notation library. And that will let you statically, in the compiler, check whether or not the big O notation of your function is what you intended it to be. And I think that that's pretty awesome, because that takes something out of a human responsibility and into automation. And I think we're going to continue to find ways to lower the cost of what the human has to do. And the more you do that, that's when you start to be able to have correctness in multiple dimensions at scale. The last thing I have on this slide is that the humans are the ultimate deciders, at least at Facebook, right? These tools, which tell you whether or not you have bugs, can have bugs. And so, you need a big red button that says, hey, I know what I'm doing. And two engineers have to work together to decide that, the person who put up the diff, the person reviewing the diff. But at the end of the day, you want to be able to ignore all of that stuff if you have to. So, great. Push the big green button, ship the code, and at that point, goes out the door. One thing that we found was kind of interesting when we analyzed, okay, we're telling people, this stuff is broken. We're telling them why it's broken now. And things are still landing, bad code is still going in that breaks stuff. Why? What are the reasons behind that? And one of the things that we kind of deduced is that people might be new to the company, or maybe they don't usually work in C++, maybe they work in a different repo, so they're not used to getting this feedback, and they don't see it. So we have these warnings now. You push the button, and builds fail, we're going to tell you. Or tests fail, I guess is what I've got here. The other kind of interesting case is I put up a diff a week ago, ran all the builds in the tests, they passed, someone said the diff is good, I waited a week or two, and then I tried to ship it. Things changed in the middle, there's no merge conflicts, but it is broken. That can happen. And so a warning turns out to be incredibly useful, and we measure people pay attention. People actually learn from this. They do then rebase their diffs. We've got a button that does that. It's just a way to minimize failures going to your code base. And this is another example of it is insufficient to tell people whether or not their code is broken, how it is broken, even if it is, whether or not they broke it, as opposed to whether or not is it globally broken, what's the return code. One of the other kind of related issues here is some people knew that their code was, a week old and might not have wanted to rebase, because if you did change string, even with a distributed build system, getting results can take a little while. And so they just didn't want to wait, because maybe there's merge conflicts in the amount of time it takes to get the results for certain things that can happen, right, for high contention files. And so an intern I have this summer wrote this awesome sanity check thing that in a really small fraction of that time build not the transitive closure of dependencies of all things that could have been affected, but the immediate ones. For our buck files as our build tool, or makefile if you're more familiar with that, what is the rule that contains exactly that header in CPP? Build that and nothing else. Don't link it, don't do anything else, just say, does it compile, is a great check to verify high level, does this look okay? And you can do that blazing fast. So again, what gets through? What are the things where stuff just flies under the radar? And one category of that is you've now introduced something that 1 in 1,000 times fails. Right? When we ran it on your diff, you got lucky. And one of the ways we address that is, again, with the wardens. There's a warden that picks up all new tests, runs them under stress test conditions, and tries to evaluate, is this a good test? And if it isn't, it gets disabled immediately. But I'll talk about another thing we do there. And the other thing that could go wrong is there is a test out there that, if it was working, would have told you broke stuff, but that test was already broken. And that's kind of an interesting category too. So for the first one, undefined behavior. Simple bug, right? One that probably many of us have written in some form or another. I allocate memory, I free memory, I use the memory in that order, right? Terrible code. And by the way, if you're of the fan club Never Write New or Delete, which I am a part of, you can still have this bug with unique pointer, right? It's just a little bit more complicated. Yes? The comment is that is something that should be caught by the compiler. I don't believe the compiler caught this one for me. Your results may vary. In any case, there's a wonderful tool out there called Address Sanitizer, ASAN. And what it does is it deterministically tells you about this bug. Right? Your program, if you run this program, it might crash, it might not, and if it was a more complicated example that actually depended on this value and the way it was changing, it might even do what you expected most of the time. And Address Sanitizer is kind of interesting in that even if your program would not terminate because of this, it will tell you about it. And the way it does that, you get a wonderful little report exactly that's very similar to this. The first line is your TLDR, heap use after free. You've misused the heap. It tells you you wrote to an invalid location in memory. It tells you you did so with something the size of an int. It tells you the line number, it tells you where it was deallocated, it tells you where it was allocated, and if you look back, it has the order exactly right. So this is kind of amazing. This is a hard to diagnose bug. At the very least, when you're talking about a real-world example, it's very hard to see usually. And that a human would have had to, in the past, figure out and understand and act on at code review. It was something that was previously not detectable automatically and non-deterministic in the way it would have shown up, is now something that you can reliably get. And not only that, it tells you why. It provides the context behind it. It shortens, a TLDR for you so that you know what's going on when you even just, begin to go looking there, which is amazing. One of the interesting things we found when we turned on address sanitizer in the code base is that it remained very kind of expert level for a long time. And the reason for that is that the output is not superhuman friendly. This is not the normal output that I'm showing right here. One example of that I'm sure you can all relate to is, suppose your stack trace contains a line that was in a function that happened to use templates, say string. String is templated over a bunch of stuff, up to and including an allocator. Maybe there's a function then that is also templated. You might have multiple templated or nested templates depending on whatever line you're in. And so a single line of your stack trace might take up multiple lines of screen real estate. And that's awful. If we go back to, I don't know, the last time you were in a class where you wrote essays, or perhaps you're more familiar with internet forums, turns out white space is very important to humans. Right? We like paragraphs, we like separation between things, we like things that are short. We're much more likely to read a paragraph than a page. And the raw ASAN output looks more like this. Right? It's 2 pages, it's got these weird hex numbers that are useful to no human ever, it's got these lines that are irrelevant and go into glibc. It's all this stuff that the normal person just doesn't care about. Maybe there's a machine that can use it more effectively than I can, but when I just want to get a sense of what's going on, 2 pages of output for this error is a little awkward. And with templates, it's impossi... So I've written a little binary, and it takes that and it rewrites it to this. And it does things like strip out templates and replace it with, less than ... greater than, so you know that there is a template there, but you just see the part that's important. And it does things like left align the file name and the line number so that you can jump exactly in the code base where you need to, and everything is not jagged. Little things like this, turns out, made it so that ASAN was not an expert level tool, was something that everyone at the code base could use. Not shown here, but we actually include a link to documentation for how to make use of the trace, which turns out to be crazy useful in every single trace. So every trace now has documentation for how to use it, which is especially useful, by the way, when somebody does something weird in, let's say, Python and gets an ASAN stack trace, and otherwise would have no idea what they're doing. So the other kind of thing that gets through is things that are already broken. And this isn't a solved area for us, but it is an area that I want to share some interesting thoughts on. At least I hope they're interesting. And that is, we have that tool that understands error messages. And if you remove information from that changes every time you run the test, like the timestamp, you can compare. Is the error message different before and after this code change in a meaningful way? And you can evaluate. Maybe you've made the problem better or worse or just different. But it's kind of this interesting idea where having the logs for exactly what went wrong in your file, in your executable, turned out to be really nice. So let's talk about what it takes to get a human to go fix something. Because you can tell them that it's broken. You can tell them why it's broken. You can tell them locally, that it's relevant to them. But in practice, we find that you need to make it so easy to go fix a bug that it's hard to ignore if you want somebody to actually address the problem. You need to have all of this stuff available to them, like the repro command. How do they fix it and replicate the results? You need the error message so that they don't even have to wait for that. They can just start fixing it. Is it ASAN or not? When did it start failing? How many things broke at the same time? Is this important enough for them to actually want to go deal with it right now? All of that turned out to be useful on the human side of the problem. How do you keep code from breaking? How do I keep trunk green? And one of the issues we had here was we were spamming people. Signal and noise is a huge issue when you're at scale, right? When you're trying to keep a code base clean, too much noise gets in the way of people paying attention to you, right? It's a classic problem. And one of the things that we used to do that was awful is we treated every single test in a binary. Suppose you have a binary with 50 different tests. When each of them fails, we would send you an email and a task, right? One for every single test. Not every file, not every problem, but just every test. And every variation of it, the ASAN one, the non-ASAN one, the GCC one, the Clang one. Tasks and emails for all of that. Wouldn't you love to get 200 push notifications for one bug? Right? Turns out our engineers didn't, and that was kind of an issue. This is kind of an issue both because it fatigues your humans, but it's also an issue because if I have 50 emails, I might just assume that they're all the same problem, but really it's 3 different ones. And I'm not going to know that until I fix the first one, wait and see that a bunch of my tasks go away, and then see that there's some more left. Right? So there's practical reasons why aggregation of your problems is important. And the way that you tell people about things is important, and we're still actually working on that. But aggregation we've actually done pretty well with. And one idea for that is you could look at the logs and say, do these error messages look the same? Turns out that that's kind of hard. And what's more, we have 3 great heuristics that you can go home and implement with probably relative ease. And the first of those was, if the ASAN and non-ASAN version of a test are failing, just assume it's the same problem, because it is. If different tests in the same binary are failing, again, same thing, just assume it's the same problem. It turns out in practice that that is the case. Right? We haven't had people complain about those aggregations ever. They just happen to work in practice. It is good enough. And the third one, which I think is brilliant, there was a colleague of mine, Kung, who came up with it, is you look for when it first started to fail. Right? Every single change to the repository has a revision. It is a single commit. And you can bisect to find out exactly when things started to fail, or you can just look at the history of, when did it go from being green to being red. And if different tests happen to start failing at the same time, it's the same problem. Put those all together, you have much higher signal. So I want to talk about one kind of hard question at scale before we wrap up, and that is, who knows about X? For a given project, for a given file, who do you talk to when it breaks? Who do you file that task on? Turned out to be a very hard question. And that might seem foreign to you if you're working in a repository that has 3 people, because odds are pretty good you wrote it or you recognize the style of the other 2 people. Or if you're working in a reasonably larger one, it might just be good enough to run Mercurial blame on it or Git blame on it. Or there's a listed maintainer. Historically, we were less good about having listed maintainers. A few years ago, that was a hard problem. Today we're better, but finding those people was a challenge. Fixing that problem means you have to answer this question. And we had some interesting ideas for how to do it, and I just want to share a few of the heuristics we used, and maybe they'll be useful to you and maybe not. One is you can absolutely look at your version control system's logs and blame, look for the reviewers if people leave the company, their managers. But more interestingly, especially for code where the authors might have left, who depends on it, and who builds it, and who deploys it are things that tell you whether or not it is relevant. They even tell you if it's dead, right? There used to be a lot of kind of dead code that we didn't know was dead. And my colleague Nicholas went on a crusade a little while ago and cleaned that all up. I think that's an interesting question that's hard. Now, before we wrap up with the conclusion, I want to give some credit where it's due. The work I'm presenting today is not all my own. It is the work of a bunch of these different teams, and it's important that I recognize that and share that with you, that this is the work of many people. And with that, I now want to wrap up. So we've talked today about these questions, and the one that I think is hardest is the first one. It's how do you prevent code from breaking? And it turns out that having the answers to all of the other questions doesn't solve it. The answers to the other questions is necessary but not sufficient. Right? It is not enough to know whether or not something's broken, why it's broken, who to talk to, all of that stuff. Because there's humans involved, and there's signal and there's noise to worry about. You need to be accurate. They need to trust you when you tell them answers to the other questions. That's hard. That's hard because 1 in 1,000 correctness for a test just isn't good enough. And that's kind of the lessons I wanted to share with you today. And with that, thanks. Yes?
You described wardens that they can ultimately detect which tests are flaky and disable them. Can you talk about that a little bit? I want to know how can developers then repro this situation locally? It's obviously intermittent, maybe happens 1 in 1,000 runs, or maybe never happening locally for the developer.
Yes.
Is there enough information for them that you provide for them to make progress on?
Absolutely. So the question is, we have these wardens that disable flaky tests, these tests where they fail 1 in 1,000 times. How then can a developer repro that to reliably fix it and know that they have in fact fixed it? And the answer is, sometimes that's easy and sometimes it's hard. We have these stress test runs. And one way you can stress test a test is to just limit the amount of resources that are available to it. So make less memory available, make less CPU available, play maybe with the network or do other things like that. You can imagine different ways that you might torture a test, basically. And there are reliable ways that you can do that, and so you can provide a command that the wardens use to figure it out, that then when people want to repro it, they have that same command to go look at and identify the same problems. Yes?
Given the fact that you can't really prevent all problems in your code, what criteria do you use if you do know about bugs? Which are the ones that you can live with, that you can ship with, and how do you make this determination?
Sure. So the question is, there will be things broken in your code. How do you decide which ones you can live with and which ones you have to go hunt down? Is that accurate? So the answer is, I'm not really all that sure. I think that depends on the team and on the product. There are certain products where shipping with a bug, depending on what that bug is, probably isn't all that important. And there's other ones that are critical, and they have, because they're critical, they have more advanced release processes that are better about catching things. So canaries and all that kind of good things that you might expect beyond the basic tests. So I don't have a great answer for that.
I have a follow-up to that question. Let's say it has always been failing, and some new code that you wrote, its execution in a testing context was short-circuited because of a test that's already failing, right? So I have point A at which a test is failing. Your code is really at point B.
Yes.
Got executed. Is that automatically flagged?
Okay, so the question is, I have a test, and if it was working, it would have gotten far enough to test the thing that I broke, but because it broke earlier, it was already broken, we didn't get there and we didn't know that the new stuff I added is also broken. And if you recall, I had a couple slides on that, but I actually don't think that they address this particular concern. It's just a hard problem. What I would suggest in that particular case is probably if you're working on code like that, you do care about the global state of that project, if not your repo, right? You don't care about the global state of the repo, but you do care about the global state of the project that you are the owner of. If I'm working on this thing, I want to make sure that all of its tests are in fact working. And so if they are broken, that will prevent me from testing the stuff that I actually care about, the change that you just made that is a little further down than the thing that was already broken. And so highlighting the projects that you care about most in the results is a good way to accomplish that. And their global state, not just is it more or less broken than it was before. Yes?
How do you get people to fix the flaky tests?
Yeah. How do we get people to fix the flaky tests? The answer is some do, some don't. And that's okay. So people have important things to do. Some tests really just might not matter. So they can live disabled forever, and that's fine. There are other cases where people say, you know, I'm comfortable with this failing a certain percent of the time, but at the very least we can tell the test infrastructure that this is a failure that's benign in some way, that it's not the responsibility of the test, that my dependency has failed. And for that we have these skips that you can say, this failure was not my fault. It was something that I depended on, and that will cover most of it. And for everyone else, for the people who really care and who want that test to be enabled, it's just up to them to go in and fix it. And we do have a team. One of our biggest products has an absolutely pristine set of tests. They have fixed every single ASAN bug, every single normal bug, they've added on their own set of extra checks. They fixed all of that. They fixed timeouts. They don't skip. It's beautiful. But not every team is like that.
So do you use static analysis on the code, and if so, how do you what is in your workflow?
Sure. So the question is, do we use static analysis, and if so, what's the workflow? The answer is, I believe so, and I don't know. Yes?
So do Facebook engineers merge branches themselves, or is there some sort of queue in the robot that will run the tests and not merge it if there's conflicts if the tests don't pass?
Yeah, so the question is, do we merge things ourselves, and what do we do if there's conflicts? And the answer is, it depends what you mean by merge. But if you're just talking about getting your changes into trunk, the land button involves continuing to try and push to the repo until it succeeds, and if there is a merge conflict, choking and telling you about it in a useful way.
How do you handle removing an API where people continually check in new uses of it?
Sure. How do you handle removing an API that people continue to add new stuff to? I have a colleague who knows a lot about that, who might be in the audience, laughing to himself. But the answer is that can be very hard depending on how big the thing is. I would start addressing that with lint. So this is dead and you shouldn't use it. And better still, one of the things that we've learned about linting is that it works not so well if you do not provide an automatic fix for people. Or in the alternative, if you don't catch it super early on before they've put any effort into doing things, quote unquote, the wrong way. So if you can provide an auto fix, if you can catch it early, that's infinitely better.
Showing test failures in sites did sound very useful, but those test failures may not be available for hours, right? The tests are still running.
Sure.
Have you ever had the chance to look at and review it before those tests are available?
So the comment is, it's useful to have the results of your tests inline on the diff for code review, but maybe they take a while to run, and what do we do about that? Turns out that almost everything runs actually pretty quickly, and so there's not a huge delay between when the diff goes up and when you have those results. But for the projects, the few of them that do take a little while, you kind of do just have to wait. I believe you can look at the logs while they're running, but that's a little bit more involved. Yes?
Can you tell me what's the reasoning behind treating flaky tests different from those that fail consistently? It sounds like if the branch is green and then there's a test failure, I could just open a bug against that, disable it, and treat it the same as flaky test. Why would I want to continue run the test?
The question is...
I need to have some detection whether it's really flaky or not.
Sure. I believe the question, and tell me if I'm right, is why would we continue to run tests that consistently fail and not disable them? And the answer is, I kind of glossed over that, but we don't. If it's consistently failing, we have ways to run them less frequently and figure out when they get fixed. Yes?
I have rather a comment about your stack trace in the test example.
Yes.
That stack trace doesn't really help with that particular test.
No, so...
Instead, you should print the context of each test case for each assertion. And there are ways to do it in Boost tests, maybe in my test as well.
So I think I followed most of that. So the comment is that the stack trace I showed in the test example way early on in the slides wasn't super useful in that case, and it really wasn't. That was a trivial example where it didn't actually add anything, but in some cases it would. And it sounds like maybe there's something in Boost that would be more useful information, is what I'm hearing.
Yeah, you provide the context of each group
Okay.
In this case, you'll bring the x is 5 or x is 3, and then you check.
Okay. I'd be interested to talk with you about that maybe after we wrap up. Yes.
How many build engineers would you recommend per engineer to be full-time? Or can you do something like this without full-time engineers?
So the question is, how many people would I have developing something like this per engineer I have at my company? And the answer is, I don't know what a good answer to that question is. Yes.
Do you differentiate, or do you detect a test has moved from error to broken and surface that, or broken is build failure?
I don't understand the question.
Do you surface to yourselves if the test used to be a error, a runtime error, and now it is a build failure?
Got it. Do we track when things go from being test errors to build errors? The answer is we have that information. I don't know if we do anything special with it. Yes?
Can you please say a couple of words about the build system you use at Facebook?
The build tool itself? The build tool itself?
Yeah, probably that's a distributed build system you developed for yourself, right?
Yeah, so the build tool we use is called Buck, and the thing that puts it over multiple machines, Buck is open source by the way, the thing that puts it over multiple machines is, well, if you have a specific question about that, I might be able to answer it, but
No, that was a general question.
I don't have a particular general answer to that.
Are you happy with it?
Yes, but everything needs improvement. Okay, so what is a reasonable turnaround time before you decide you want to distribute the builds and the tests? The answer is we were doing that before I arrived, so I never really felt that pain. But I can tell you, there's a decision that I make as an engineer. Do I want to build this locally on my box or send it off for review and also get all those builds that way? And my heuristic usually is run the test or two that's most important to me, and then toss it up and see the rest of the results. Right? I make sure that a small sample size works, and then I get the global results and see what's going on. And of course, those first couple tests are usually pretty fast, and when you build it once, the incremental build time is then very small.
Question about the smartness of wordings. Imagine that you're making a change to the test framework itself, similar to the one that you showed us in the beginning.
Yes.
And then there's an undefined behavior in what you submitted that will affect, let's say, about a few percent of your entire test suite, but you discovered it much later on. Would the wardens file backs against individual owners for this test, or would they be able to somehow figure out that they might be related to the framework changes?
Yeah, so the question is, suppose I break the testing framework itself, cause a certain percentage of all tests to fail. Who gets blamed in that situation? Who gets the task? Me for breaking the test framework or the test owners? And if there's a bisect, it probably goes to me.
Do you have any plans to open source your tool to improve the way the call stack looks?
ASAN? Yeah, I've gotten that question before. I have no firm plans to do it, but it isn't something that I think I or the company would be opposed to, so that might happen at some point, but I don't have it available today. I can tell you that the implementation, for the most part, is just a bunch of regexes to remove things that humans don't care about. So, it's something that could be whipped up at home too, but I might look into open sourcing it, but I make no promises.
You said Buck was open source, but the review board software you use, is it open source as well, or is it homegrown?
The which thing? Oh, Fabricator. A version of Fabricator is open source. Internally, we use one that's a little different.
I have a follow-up question to the question I just asked. You said bisect. How would that be possible if the tests were failing intermittently? So
Yeah.
We're able to submit. You don't have consistent failures.
Yes. So he's saying for his old question, where you break the testing framework and you bisect, how can the bisect be successful when the breakage is non-deterministic? It depends how good your system is. There are papers out there, if you Google for it, for how to do flaky bisects, where it fails some of the time but not all of the time, and you could use one of those to figure it out.
So at Google, you can say runs per test. And so if you're like, it fails more than 100 times, instead runs per test to 10,000. And the bisect will find it.
Yeah. Yes?
You gave the impression that developers are free to disregard the output. Is that true?
So the question is, are developers free to disregard lint output? And the answer to that is yes, you can ignore it if you know better. Ideally, all of your lint is high actionable things that you want to listen to, but sometimes maybe that isn't. So
There's no category where you have to fix things.
the question is there a category where you have to fix things? And this goes back to, you have these automatic correctness checks that try and find bugs for you, that they themselves might be buggy. And so there always needs to be an escape hatch. So that's my answer to that.
So to make the decision, do the test wardens also have access to the test coverage stacks?
So do the wardens have access to test coverage statistics? I'm not sure why those two things are necessarily related, but maybe let's talk about that after. I'll take maybe a couple more questions and then let's call it quits.
From what you showed us today, what's available for us to use in terms of tooling? How about that automatic code review tool?
Yeah, so what's open source from what I talked about today? The answer is, unfortunately, probably not a lot. So Fabricator itself is, Buck is, the distributed build thing, not so much. The goal of this was to talk about lessons learned, but not everything is open source. So I believe the question was, correct me if I'm wrong, how do you merge all of your projects together in the main branch, and how do you test that? I don't have a great answer for you. I think we are operating on a different model than the one you're used to. Let me leave it at that.
I'm curious on the wardens. Is like writing and adding a new warden something that's very easy for any developer to do? Is it something that you would have like a list of them that you potentially could open source or applicable with a wide range of developers? How does that exactly work?
Sure. The question is, how easy is it to add a warden, and how easy would it be to open source one? The answer is it will soon be much easier, and open source isn't currently on the agenda for that particular team, for that particular product. And I think I'm going to call it there. Thanks again.